All right, hello again, everybody. We are moving on from the last chapter where we kind of were thinking about the power series transform, Fourier series transform, which sent us into, it took functions and mapped them to vectors, infinitely large vectors, and then it mapped operators into matrices. And today we're going to extend this now to what I'm calling continuous transforms, in the sense that instead of having a matrix, and I'll write this down a little bit clearly here, instead of a vector and matrix, where we think about the vector, you can either say like, okay, it's a0, a1, dot, 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 an, dot, dot, dot. So that's a vector, which, you can represent as a sequence. And now this is n in like the natural numbers, maybe including 0. So the vector is like a sequence. A matrix then looks like m11, m12 dots, m1n dots. If it's an infinitely large matrix, right? 2, 1 dots, mn1 dots, and then down the diagonal we have something like mnn, and so on. We can associate this kind of, in some sense, it's also like a sequence. I'll say j, k or something. J is in the natural numbers, including 0. Maybe I should have started at 0, but it's fine. J is in the natural numbers, k is in the natural numbers. Right, so in some sense, these vectors are numbers. Oops, I wanted a highlighter there. They're numbers indexed over kind of a discrete set, even though it's an infinitely large set. And matrices are numbers indexed over 2 discrete sets. Today, we're going to be reinterpreting the continuous, or the continuum version of this would be something like a sub x, where now x is in R, and the continuum version of this is now like m sub x y, where x is in R and y is in R. Okay, so now we're basically saying, what does the continuum do to vectors? Well, it turns them into some numbers indexed by the real numbers. And what does the continuum do to matrices? It's now numbers indexed by the real numbers. And okay, I'm going one step further. What am I really trying to do here? This is just a function of x. This is, I'm going to call it k, x and y. We call that the integral transform kernel. But in some sense, what's happening is that the continuum version of functions as vectors is just a new function, and the continuum version of matrices is a 2-dimensional function. So now we want to think about transform methods, transforms, and in particular, these are integral transforms. Integral transforms, they take some function of a variable to another function, and maybe I'll call this f of y here, a function of a new variable. Maybe I'll say that z here even or something. And operators, they take L, some linear operator, to functions of 2 variables. So that's the useful thing about continuous transforms, is we get new functions go to functions, which is fine, but kind of the really special thing is that operators go to functions. And that is incredibly powerful, right? Because the moment that an operator, this is really a function with multiplication sitting around there. The moment that an operator now gets sent to a function with multiplication, operator inversion goes to inverses with respect to multiplication, which are very easy to compute. And this is really the beauty of these transform methods, right? The discrete transform methods took operators to matrices, and I know how to compute inverses of matrices. That's linear algebra for you. But now in this case, the continuous transform is going to take an operator to a function of 2 variables, and actually sometimes just a function of 1 variable. Maybe I should make that a little clearer. A lot of times it only takes you to functions of 1 variable, in which case we have true just function inversion in the sense of inversion via multiplication, which is just 1 divided by that function. So this is where continuous transform methods get really, really useful for us. Okay, so jumping away from kind of that super motivation, let's actually head into what's going on here. Another reason why continuous transform methods are important is this thing that I was mentioning in kind of our Galerkin method part, where I said Fourier series methods require periodic boundary conditions, and I'm just reiterating that here. So if we're trying to solve maybe an IVP, which is not periodic, I want to solve an IVP infinitely far into the future, you either had the choice of taking a maximum future time t1 and then doing some sort of Fourier series over an interval larger than that, and then you're periodic on like that bigger interval, but that still doesn't feel right, because if we're predicting things about the future, we would want to go as far as we possibly can. And so what we're going to do is we're going to take this epsilon on my interval and we're going to push it to infinity. So really I'm going to recover now an interval t0 to infinity, but that's going to force me into this idea of a continuous transform, or thinking about the boundary conditions. If I'm doing a BVP on some x0, x1, I tried to make a larger interval in which I was periodic over the larger interval, and then fit myself to x0, x1, and then if I take epsilon to infinity on this larger interval, all of a sudden I'm really doing like a Fourier series over the interval minus infinity to plus infinity, and that's also going to recover us a continuous transform. But we're going to get two different continuous transforms. Okay, so this transform over t0 to infinity, that's going to give me the Laplace transform, and then the transform from minus infinity to plus infinity is what's going to give me the Fourier transform. You'll see I crossed out the word series to basically say this is the Fourier transform that other people refer to as the Fourier transform. But today we're going to restrict ourselves to the Laplace transform. So let's jump back to kind of this overarching idea of the Fourier space, because this is where our original Fourier series transform came from. And it's defined on the interval t0 to t1 as the following. I'm sure we're all very familiar with that by now. And the coefficients in this space, which are really the elements of my vector, are given by the integral 1 divided by t1 minus t0 and then the integral from t0 to t1 of it's my function against the Fourier basis. Well, what I want to do, according to my remark, is go on this interval t0 to infinity. So somehow I want to take the limit as t1 goes to infinity. And I have to take that limit right here. I have to take the limit right there. I have to take the limit right there. And I have to take the limit right there. So if I'm representing f of t with t1 going to infinity, there's 1, 2, 3, 4 places that it's going to push itself to infinity. And actually, I'm going to let t0 be 0 for some ease. We'll see eventually how to shift away from t0 being 0, but we should stick with t0 0. Okay, so what I'm doing here is I'm re-representing this expression. I'm plugging the specific expression for a in there, and I'm keeping everything else the same, and I'm letting t0 become 0. And that's why my denominators have shifted to just t1, and then my upper integral bound has also shifted to t1. Okay. But once I do that, then I'm going to try to compute what does this expression turn into as I shift t1 here, 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 and here all the way out to infinity. What happens to this expression? Well, what I can do is I can reinterpret that infinity and that infinity as a capital N. This is how we define infinite sums, right? And we let the capital N tend to infinity of that infinite sum. But then I have to do something a little bit clever, and it's maybe not so clear that I should be able to do this, but I tell myself, hey, those are both going to infinity. Both of these limits are going to infinity. Now, one line above, or even in this line, they go to infinity separately, but let's couple them together. Maybe this is a question I ask. Is there a useful coupling of t to n as they both tend to infinity? Is there maybe a direction? In some sense, I can think about it as a two-dimensional space where I'm heading out to the infinity in the upper right quadrant. Is there a direction in that upper right quadrant where I can gain maybe some more useful knowledge? And the answer is yes. So that coupling is going to be 2 pi n to the 1/2. And basically, you choose this so that you get something useful out of it. Otherwise, you could try to take t1 to infinity of this expression, and nothing necessarily will show up that's useful. But if you pull it out and you kind of say, I'm going to take these to infinity together at the same time, we're really just taking now capital N to infinity of the sum, and now some 2 pi's are showing up, and some root powers of n, so n to the 1/2 are showing up. And it's not so clear, but if we think about it, this 1 over n to the 1/2 is tending to 0, and I have an infinite sum over something that tends to 0. This is exactly the improper Riemann integral, right? This is like, here, this is like delta, I'll say delta x. This is like x0 to x. This is really n to the 1/2 x0, n to the 1/2 x1. Those are my limit bounds there, and then this is tending to infinity. And then I'm performing sums over these terms that are tending to 0, right? So these are each like continuum x, I should say, continuum, or something. Maybe I'll use an s instead of an x for each of these. And then it shows up better in our next line. So s naught, s1, continuum in s, and then there's like a ds at the end. That's actually a Riemann integral, and it's the Riemann integral that looks like the following: 1 over 2 pi minus infinity to infinity. That's coming from this sum right here. So the sum, because the ds was only a power of 1/2, there's a power of, this is basically n to the 1/2 squared. So one of the n to the 1/2 is just becoming s, but the other one is jumping out to plus and minus infinity, and that's why we get the integral to plus and minus infinity right here. And we get ds right there. And then this turns into s, n divided by n to the 1/2, and n divided by n to the 1/2 both become s. So this is becoming s, this is becoming s, this is becoming ds, this is becoming infinity, this is becoming minus infinity, and that's becoming infinity. So that's what's going on here if I take that particular limit, and in doing so, we recover kind of this identity for f. All this is doing is it's re-representing f. It says, hey, I can represent f as the interaction of two integrals, two independent integrals against each other. I have this inside integral and I have the outside integral, and they cancel each other out. But what's cool about that is that if I then say, okay, what is this? What is this? If I decide to call that inside integral something else, then I gain some useful properties about that inside thing. Oh, and there's one extra. There's one extra thing that I should talk about, and that's that it becomes a little bit useful to take the inner integral to be purely real. Okay, so right now I have e to the minus ist. This is still perfectly valid, but what I can do is I can take the is's here, and I can say let is map to s, and what I get out of this is I have to integrate over some imaginary bounds on the outside integral, and I also have to divide by s. But what I get that's useful is that all of a sudden this is a purely real inside integral. And that purely real inside integral, we're going to give a name, give it the name capital F of s, because it's integrating over the dt, so it is a function of s. So I'm going to give that the name capital F of s, and then I have this nice property that I can recover lowercase f by taking a complex integral against capital F, and I can recover capital F by computing a real integral against lowercase f. And it turns out that this second case here, this is our Laplace transform, and that's its inverse. So let's jump down now to the definition. The Laplace transform is precisely that inside integral where I compute from 0 to infinity f of t e to the minus st dt. And this will be a function of s that we often denote with a capital F. So that's going to be some other function of the variable s, because s hasn't been determined for me yet, and capital F depends on lowercase f. Its domain ends up being this space of, at most, exponentially growing functions. Basically what that means is if I let the parameter in exponential decay get large enough, if I choose some really, really big s sub 0, then I can gain that the limit of f times exponential decay is 0. So that means that f at most grows exponentially, because maybe it's exponential of order 34, then the moment s0 becomes 35, the entire limit has to be 0. So those are the sorts of functions that I can plug into my expression there. And directly from the above, so from right here, we have our inverse Laplace transform. So the inverse Laplace transform is given by this complex integral, which I write on the bottom there for you. And actually I've thrown a gamma in there. It's not clear why I should be able to throw a gamma in here. This gets into some pretty deep complex analysis. But actually all I have to do is take a gamma in R, for which capital F, which you'll recall was this, is analytic at gamma plus is for all s. So once it's analytic in that entire vertical strip, I guess, so I'm integrating f over a vertical strip in the complex plane. The moment that I grab a gamma for which that's well defined, I can compute this integral. It's also not clear that it should converge, but it does. So yeah, there's a remark talking about that a little bit more. So don't worry too much about the inverse. We won't be using, I should write this down for you. We will either calculate inverses with a computer or with a table of transforms. And what do I mean by this table of transforms? Maybe I'll jump there right now. So how will we actually be computing inverses? First of all, you should agree with me that computing forward transforms is not that hard. This is an integral that you should be able to compute for a lot of functions f. The inverse is the tricky one. I'm going to jump to the end of the chapter. So here I go, all the way down. We start to see, before the exercises, tables here. Okay, so I've got section 9.7, I say a table of Laplace transforms. And it says the following table uses the definitions, and he gives the definition of the forward Laplace transform that I gave above, and that's also known as capital F, and the reverse transform, or the inverse transform, which is that ugly complex one, and that's lowercase f, as long as it acts on capital F. And then really what we want to think about when we look at these tables is we tell ourselves, okay, if I start with this, then it pushes me over underneath the Laplace transform, L, script L. It pushes me to the right-hand side to the following function. So if I look at the bottom here, if I start with t to the n times a function, then the Laplace transform pushes me to negative 1 to the n power n derivatives on the transform of f, right? So this is basically saying, hey, you can compute Laplace transforms of products with monomials using derivatives in like the transform space, and vice versa. So and then if we were maybe trying to invert a function, let's say we wanted to invert, if I start here instead, then I can take an L inverse, script L inverse, and I can end up here. So you end up there under the inverse. That's the idea of doing transform tables. And so the transform tables are never going to contain every single function that you want to invert, but they normally contain a good amount of functions, so which if you're clever about rearranging whatever you're trying to invert, you can use pieces of the table together. So I'll say this on the side. Laplace transform inversion is equivalent to rearranging / simplifying what we want to invert until it shows up here on the right. So that's what we're going to do. That's how we're going to invert things. Is we're going to take some function and we're going to manipulate it until it shows up as maybe some combination of those, or if I scroll down, maybe some combination of those. Right? So these are separated. The tables are separated with that horizontal line. Everything on the top half of the table is like theoretical. I've kept everything with f's and g's and like very theoretical functions. These are just like generic functions in general and how they transform, kind of what the process of a transform looks like with generic functions. And then I've provided some specifics in the bottom half. So if I look at some specific functions here, don't worry about like the delta or the h yet, but I can look at like my specific function. If I'm transforming the specific function t to the n over n factorial, it transforms to 1 over s to the n plus 1. If I'm transforming the specific function sine of lambda t, that becomes lambda over s squared plus lambda squared. So there's all the specifics. I can think about it. I can just do a quick example for you. Let's just say L inverse. So you get what I'm saying about something like this. If I do L inverse of maybe e to the minus 7s lambda over, I should use some real numbers, 3 over s squared plus 9. Okay, we want to interpret the 9 as 3 squared, and then I have a 3 on top, so I'm looking at this piece, 3 over s squared plus 9, that looks just like sine, but then I somehow have to compensate for multiplying by e to the minus 7s, and if I scroll up, I see that compensating by multiplication by e to the minus something gives me f of t minus that thing, and then this h function, which we'll talk about later. So this would be something like sine of 3 t minus 7 times this h thing, t minus 7. Okay, so that's how we would compute an L inverse. And we'll go through it a little bit more in class about how that really works. But that's how we want to think about this table. It's just like I use a combination of what's on the left-hand side and the right-hand side to give me the inverse, to work back and forth from the right to the left. Okay, so jumping back to the section that we actually care about here today, which is section 9.1. Let's talk about if this truly is a transform, right? If this truly is a transform, then somehow I must be able to represent linear operators L under the transform, right? In our previous transforms, these L's were turning into M's, capital M's, they were matrices, and I represented the matrices by computing some inner products of of my operator against like basis elements. Well, here we have to be a little bit more clever, and this is a general theorem that I'm not really going to talk about, but you can read it. If I jump down to the Laplace transform version, we have to be a little bit more clever about what is that inner product with the basis functions. Well, it looks like this. This is my inner product of L of E tau comma ES. Okay, it looks like that in the Laplace transform world. And when I do that, I gain this function of two variables, right? We'll notice that here, both tau and s have not been determined yet. And so if I integrate over t, I get a function of s and tau. And then my representation, this is the representation of L in the Laplace transform space. The representation of L in there looks like this. And so it's a little bit ugly. You can see I basically have the inverse transform sitting around in there. But this is all very theoretical because now we're going to actually go through computing some representations. Right? So ideally for let's say for ODEs, I want to represent two things, right? I want to represent my derivative. I want to represent multiplying by a function. This is the same way it was in the last chapter. I want to represent two very particular linear operators. One of them is the derivative, the other one's multiplication by a function. Let's see what those look like. And here we go. The derivative, this is the nth derivative. I put a nice wide tilde over these if I'm talking about their representation. So the representation of the derivative is multiplication by n powers of s. So it's a monomial in s. So there's my Laplace transform function, but now my representation of the derivative is n powers of s minus a sum of my initial conditions. That's what I should think about here. So derivative, or really n derivatives, is multiplication by s to the n and subtracting a polynomial of initial conditions. So this is a negative polynomial of initial conditions. So I have this multiplication by something, and then I actually end up with a polynomial of initial conditions sitting around in my transform space. This is pretty useful though, because it throws initial conditions right into the problem for me. And then when I invert things with the Laplace transform, the problem with initial conditions is already solved. So that's how I solve problems with the Laplace transform. And then if I scroll down and look at the multiplication operator, the representation of multiplying by a monomial, t to the n, is -1 to the n and then n derivatives on f. Okay, so this is how I represent this multiplication in the Laplace space. So this is now my version of the matrix that I had in the discrete case. My version of it is now -1 to the n and then n derivatives on f. Now because of this, I'm going to bring up a remark, or I guess I call it an example, but because of this, the remark is that the Laplace transform is pretty poorly behaved for general multiplication operators. If you think about it, if I grab some general multiplication operator g, then in the transform space it looks like the infinite. If it's analytic at 0, then it's the infinite sum of derivatives. So that's pretty bad. That's pretty not something that I want to consider. There's also a way to represent this with convolution. Can alternatively represent with convolution, but it doesn't get any better, and you don't even know what the continuous convolution is yet. We'll get there eventually. But your table at the end of the book does represent this with convolution. Maybe I'll jump there right now to show you that you can also represent it with convolution. Wow, what a good way to get down. All right, so here you can see that if I multiply f and g together in the natural space, you can alternatively represent it with this is called a convolution, a continuous convolution over my complex integrals. So it's not necessarily any better written in this case. You know, there's not really a good way to do it. So we don't really want to consider linear differential equations with like super generic functions here, g's of t's that are multiplying my original ODE, or something like this. If I start with my ODE, that's like, you know, y prime plus m ty equals 0, when I transform this whole thing, that term is going to get really ugly if it's not just a polynomial. If it's a polynomial, then I can usually play around with it and I'll be okay. But if it's not a polynomial, then I'm kind of stuck. All right. So basically the last thing that I want to say then is what sorts of ODEs the Laplace transform can solve and how we might go about doing that in a step-by-step process. So this is kind of like the pre-Laplace transform section, then we'll get into actually doing this in the next section. So because of this, what we can solve with Laplace transform is higher order ODEs with polynomial coefficients. Okay, so we only allow ourselves coefficients with polynomials, but this is nice because it encompasses both constant coefficient and Cauchy-Euler type ODEs. So that's useful, as well as some others, right? So they're more exotic polynomials that we could put in front of our ODEs. Another one that's useful is going to be in systems, higher dimension than 1, and we'll run into one of these later. And then there's this thing called impulse forcings, which I'm calling non-smooth forcings. And this is a case where we're kind of going to jump our way outside of analytic functions now, where we're going to give ourselves some forcings that are no longer analytic, and things behave considerably differently when you run into non-analytic forcings. So we'll get there eventually as well. And then the last proposition is, okay, how do I actually go about solving something with the Laplace transform? Well, you just start with an ODE, which actually has to be an IVP. So Laplace transforms and IVPs, maybe I'll write this down. Laplace, if and only if, IVP. Okay, so we want to use Laplace for IVPs. And so I'm given an IVP here. It's an nth order IVP. I'm using capital N here instead of lowercase m. I don't really know why I decided to change notation there. Oh, I see. It's because it's a matrix. So this is a collection of matrices because I'm in higher dimensions. So I have this higher dimensional linear IVP, and there's my initial conditions given to me at 0. For now, we're going to stick to Laplace has initial conditions at 0. And what I'm going to do is I'm going to calculate the Laplace space representation of these j derivatives and multiplication by these m matrices, and I'm going to call that a symbol. Okay, so I use this as a footnote. The transform space representation of an operator is often called the symbol. So I'm going to call this the symbol of the operations on y. And then what I get as my solution to the differential equation is pretty easy because all I have to do is I take the Laplace transform of the right-hand side, Laplace of right-hand side. I then compute the inverse of the symbol. So I invert the symbol, which is just the Laplace space representation of kind of what's happening here on the right-hand side, those operators on the right-hand side. So I invert that symbol, and then I transform back, okay? And then I finish by inverting the transform. So I invert the Laplace transform. And this is how we're going to go about solving IVPs with the Laplace transform. It's always 3 steps. Step 1 is always the Laplace of the right-hand side. Step 2 is always construct the symbol and invert it, right? There's an inverse there. Step 3 is always take the inverse Laplace transform of everything. So those are the 3 steps to solving a Laplace transform. I provide it in step-by-step form right there. Take the Laplace transform on both sides, collect all terms with the transform of y on the left-hand side, factor out Ly to the right of those terms. You should end up with something like this. You'll have the symbol times the Laplace transform of y equals the Laplace transform of f, and then I'm going to invert the symbol, and then I'm going to invert the transform of y. And so this is another representation of what I'd written in my proposition. It's the transform of f, the inverse of the symbol, the inverse transform of everything gives me y. All right, thanks for sticking with me. It was a bit of a longer video today, but I'm glad to go through it. Anyway, I'll see you later. Bye.